Hello everyone, we're looking at reliability and validity this week, so let's go ahead and jump on in. So measuring the data as we collect it is certainly an important topic. Poor measurement is going to lead to poor results internally and internally, but it also brings in this concept of reliability. How well will the measurements we take on one case equal the measurements we get in the next time? And if you've ever gone on a diet, you'll know the importance of reliability or the frustrations of unreliability as you go from different scales. You would certainly want a reliable measure in weight loss and in research. So we're going to look at some central tendency measures, some measures of spread, and then get into the validity and reliability issue a bit more. So data comes in four shapes and sizes. The earlier chapters of your book really looked at two types of data. One would be categorical, and the other is continuous. Now here we break those into a little more finer grain. So those categorical variables could either be nominal, so what color is your hair? What type of car do you drive? What is your favorite music group? Things like these. There's a name. The categories have names, not meaningful numbers. Ordinal, on the other hand, is also somewhat categorical, but the first place, the second place, the third place. And the reason why we call them categories is because there's not necessarily an equal interval in between them. So you might have the first place runner in a marathon be way out in front, and then the second and third are immediately right after each other. So between first and second, there's a huge gap. Second and third, there's a tiny gap. So because rankings like that, places, don't tell you the interval in between them, it's also considered a category. And then these last two, interval and ratio, the main difference that we have between these two is that both of these would be considered continuous in the sense of what we looked at in earlier chapters. But the ratio is going to have some sort of meaningful zero or some sort of absolute zero, which then allows the numbers to be multiplied by factors. Whereas interval, we can only add and subtract. Ratio numbers, if we're manipulating the data, we can also multiply, which gives us an additional range of tests that we can use. So central tendency, when we describe data, and now we're talking about, here we're talking about more the continuous types of data. I guess I shouldn't say that always. The mode is going to appear in any of the types of data, but the median and mean, we mean continuous types of data. And the mode is whatever shows up the most. Median is the 50th percentile. You're right above half the data and right below half the data. So if there's 500 people who took a test, the student who is at the 50th percentile would be right in the middle. It'd score higher than 250, lower than 250. I guess that makes 501, but you get the drift. It's right in the middle of the number. Whereas the mean, which we also use the word middle for, is a mathematical definition where we add up all the values and divide by the number of values there are. So, for example, you could have people in our class with salaries ranging from $20,000 to $1 million. I don't know if anyone in our class is that fortunate, but perhaps. So instead of the median being around 500,000, which is what you might expect because it's halfway between those two values, the mean might just be something like 30,000. And the way that we can do that is because so many of us have lower salaries, myself included, that even if you have one or two high outliers, it pulls the value up, but it doesn't. We're certainly not going to be all the way halfway there. I think a picture might help at this point. So if we look at three different distributions, so wherever the graph is higher, that means there's more people. So in a standard normal, you'll have the mean equal the median. Here you can see that the median is a bit lower than the mean. Why is that? It's because these outliers right here are pulling up the value of the mean. Outliers are not going to affect the median. Why is that? Because if the richest person in the class has $30,000 salary versus the richest person has a $1 million salary, it's still just one person. So when we're looking at median, all we're doing is looking at the ranking. It doesn't matter how much behind the first person you are, the second or third, whereas mean is going to mathematically figure in every single value. So this is actually the opposite case of what I had just mentioned on the slide before. In this B here, we have these outliers being so high that they pull the mean up without affecting the median. On the other hand, here we have, this is called a negatively skewed graph. This over here was a positively. Notice it's backwards of what you might think because it refers to the tail, where the tail is. So here the tail is in the negative direction, and these outliers here pull the mean down below the median. So mean and median will not line up typically, except in a symmetrical distribution. Okay. Variability is more how spread out the data are. So measures of center, what's the middle? Variability, how spread out is the data? Range just gives you the lowest to highest, the difference between those two. Standard deviation is a much more specific calculation. And in this class, I'm not concerned as much that you know that exact formula as just the general sense that it's about the average distance away from the mean. And when we say average, we don't mean the arithmetic mean like we were just talking about, but maybe we should say the typical distance between the data points and the mean. How spread out are the data? And in a normal distribution, we have some very specific relationships. So in a normal distribution, we'll have 68% of the data within plus or minus one standard deviation of the mean. Within 2 standard deviations, we'll capture 95% of the data, and within 3 standard deviations of the mean, we'll capture 99% of the data, over 99% actually. And you can see as we go out more and more, we have less and less. So where is this used? For an example, let's take IQ tests. Originally, the mean IQ was set to be 100 with a standard deviation of about 15 in the US. And here, remember we were talking about populations last video. So IQ is an interesting one because in different populations, for example, the Korean population, the average IQ is higher than in the US population. So it's important for agencies like who are looking at gifted students, for example, or students on the lower end of the IQ scale, because you want to be relative to the population you're in. So, for example, Mensa has a criteria. It's a gifted organization. You have to be at least 2 standard deviations above the mean, and I believe that's specific for your country. So if you're in the US, the mean's 100, standard deviation's 15, so 2 standard deviations would be 130, so you'd have to have an IQ of 130 or higher to enter Mensa. And the nice thing about these measuring things in terms of standard deviations is we don't care about the units, whether they're inches or centimeters or degrees Fahrenheit or some kind of measure that we micropixels or something like that you're not even sure quite what it means. But if you know how many standard deviations above or below the mean you can compare things without even understanding the units. If a person is 1.5 standard deviations above the mean in terms of height and only 1 standard deviation above the mean in terms of weight, we would say that that person, their height is more unusual in the population than their weight in a normal distribution. So let's jump on here. Okay, the final topic here is reliability and, we have one more slide, sorry. Correlation, just showing how well two things go together. So we just ended on height and weight. This is a great example. If you're above the mean on height, do you tend to be above the mean on weight? And the answer is yes. Will you always be? No. But it is a fairly strong correlation, height and weight. The taller you are, the more you tend to weigh, and vice versa. Does not mean that one is causing the other. So let's say higher amount of crime in a city, higher numbers of crime, will also correlate with higher numbers of churches. This is a classic study. That does not mean that religion causes crime or that crime causes religion. In reality, both of them are probably just highly correlated with a population increase. The higher the population, the more churches, higher population, more crime. So correlation goes from -1 to 1. 0 means no correlation. And as you move out towards either -1 or 1, that's a stronger correlation. Positive means as one variable goes up, the other variables goes up, like height and weight. Negative correlation, as one goes up, the other goes down. For example, we might have, should have thought of this before I started the video. Might have something like height and ability to crawl through a tunnel. The higher you are, the smaller your ability to crawl through the tunnel. That's weak, I know. So correlation just is the relationship between the two variables. Validity, important. The extent to which a measure measures what it's supposed to measure, what it's intended to measure, versus reliability, how well something measures data from time to time. If you do it now and then again, if you can see, you probably cannot see that. I'm going backwards here. Okay, there. This clock behind my head there is stuck at 9:45. It's been 9:45 for the past year, according to that clock. It is an extremely reliable clock. Every time I look at that clock, it is 9:45. It's a horribly invalid measure. That clock is not valid at all. Well, it's valid 2 times a day, I guess you could say. Once in the day, once in the night. But it's always predictable. It's giving me the same reading every time. Here's a graph that kind of shows you. So this is my clock here. So it's giving me the same time. Actually, my clock would be right on the money every time. Versus something that's valid, but not that reliable. So if you have a clock that is telling you time, but sometimes speeds up or sometimes slows down, that's not very common. But if you had that, that would be valid. So it's telling you an approximate time, but it's not very consistent in the values it's giving you. Something that's not reliable or valid is not much help. And something both reliable and valid is obviously what we want in research. So I would say that validity is more important in research, but it's very hard to measure. Reliability is very mathematical, and so you'll see that a lot more. And that's about it for today.